Welcome to the LemnaTec Academy. In this video, I will explain the chlorophyll fluorescence analysis using LemnaTec systems and LemnaGrid. We use a variety of different sensors for chlorophyll fluorescence from different vendors in our systems. The decision which sensor is used is made when the system is designed. It depends on factors like plant size, field of view, etc. For instance, in a HyperExpert, the sensor is moving to the sample in a relatively small enclosure. This requires a different sensor than in a conveyor system for large plants and a much larger imaging cabinet. That said, all systems create a series of images or frames which differ in meaning and can be identified by name. Usually, we find images for fluorescence in the dark after dark adaptation, called F0, maximum fluorescence after dark adaptation, called FM, base fluorescence after adaptation to light, called Fs', and maximum fluorescence after adaptation to light, called Fm'. For some of these frames, other names are also used depending on who you ask. In this video, I will use FM0, FM, Fs', and Fm'. Some sensors create additional images. For instance, they record light curves with varying actinic light and therefore create multiple instances of Fs' and Fm'. Others record images representing the chlorophyll content. Others again record red, green, and blue frames to reconstruct an RGB image. And there are more options in some other sensors. In this video, however, I will focus on these four alone. So without further ado, let's go into LemnaGrid. First, we need to load these images. The name of these files depend on the system and the sensor. Please refer to the system's documentation and the training session for details. On the system we use as an example in this video, they are called PMT-F0, PMT-FM, PMT-Fs', and PMT-Fm'. All are TIFF files. We will add one disk universal reader for each of them. Because we have to support legacy systems, we need to convert these TIFF data into actual grayscale images. We use a demosaicing device from the camera support group. In this device, we select NO for no further action. We have to do this for all four readers. Depending on your system and sensor, these images might be stored as 8-bit PNG files instead of the 16-bit TIFF files we have here. In this case, the output of the disk universal reader is technically an RGB image. This is from a different sensor. Therefore, we need to convert it into a grayscale image. Since the RGB image is effectively a grayscale image, all color channels have the same value. Therefore, it is best to use one of them, for example, the red channel. This avoids unnecessary numerical errors when we mix different channels. In this example, we will use the TIFF images, so we can remove these two devices. Before we start with the measurement of values like Fv over Fm, we need to detect our plants. In other words, we have to do the segmentation. At first, I will use the Fm signal for the segmentation. We use here a simple threshold device. In this case, a threshold of 20 seems to be reasonable. Higher values will remove parts of the plant. Lower values will include too much background. Now we add the usual morphological cleaning process. First, we add a multi-step morphological device. We use subpixel accuracy and first subtract 2, add 4, and subtract 3 again. This reduces the size a tiny bit. We do this to avoid the accidental inclusion of background pixels at the edges. Finally, we add a fill areas device. Images from chlorophyll fluorescence sensors are usually lower resolution than typical RGB images. Therefore, the size of the holes to be removed is smaller as well. In our case, a size of 20 pixels works well. In other cases, values up to 100 might be reasonable. However, if we measure dark and light adapted scenarios and other parameters, the measurement time can be quite long. The plant may move ever so slightly during this time in response to the actinic light. Therefore, you may want to use other channels than Fm for the segmentation or a combination of multiple channels. For instance, we may use Fm prime for parameters based on later recording stages, like the Y2 parameter. "16" seems to be a good threshold in this case. We shall consider a combination of both segmentations for parameters like NPQ, which use data from early and late stages. We use the logical operations device from the logical operations group to merge them. We combine them using the AND operation, which means that only those pixels are part of the segmentation which are found in either of the previous segmentations. Now we can convert them into object lists and merge them into one object. I add a loop-through device for reasons which become obvious later. Use the same for the other two segmentations. Now we can start with the calculations. The first parameter we look at is Fv over Fm. But first I like to add a few loop-through devices. We use a gray calculator to calculate FV over Fm. You find this device in the arithmetics group. We connect the F0 and Fm images to the two ports. F0 is connected to the first port and will become variable A in the formula. Fm is connected to the second port and will become variable B. The formula for Fv over Fm is Fm minus F0 divided by Fm. Remember, F0 is now variable A and Fm is now variable B. So it's B minus A divided by B. I add a small number in the denominator for numerical protection. This number helps to avoid infinity for pixels where Fm is 0. This number shall be significantly smaller than 1, but also not too small that dividing by it does not get too large. 1/1000th is a good compromise. At first glance, the result is unexpected and disappointing. We see only black. This is because the value of Fv over Fm is between 0 and 1. But LemnaGrid assumes values between 0 and 255 for its images. We can see the values if we use the tooltip. We may add a factor of 255 to get a better image. Now we see the calculation results. In the background, we see a lot of bright pixels. These are divisions by 0, or more precisely, divisions by our small protective value. We will get rid of them later, but I will return to the original scale with values between 0 and 1. In order to get the measurement into the result data, we need the mean color property device. We use the objects from the segmentation and the values we just calculated for the Fv, Fm as color information. Now we can send the result to an object writer. The object writer needs also an image to visualize the result. Therefore, we need to amplify the output of our Fv/Fm calculation by a factor of 255. This makes the value of Fv over Fm equals 1 to be bright white. I use the gray calculator to do this. This time I reduce the number of inputs to 1. This error at this point is normal because we have only one input, but our formula requires 2. This simple formula amplifies our image. We could use also a factor of 100. Then the values in the image represent Fv over M more conveniently. For example, a value of 0.67 is represented by 767. If we multiply by 255, it would be 171. The downside is that the image is much dimmer. For this video, I will stick to 255. We also need to get rid of all the background pixels. These values are not very well defined. F0 and Fm are basically background noise. Therefore, F0 might be larger than Fm, and Fm might even get to 0. Therefore, we will mask them out using the image mask device from the logical operations group. This looks a lot better now. The object writer requires an RGB image as input. Therefore, we need a universal converter to convert our grayscale image back to RGB. Now we can design our result image. Sometimes a false color image is favored. We can use a palette gray to color device from the gray to color conversion group. We have a few palettes to choose from. This device will replace the universal converter. There are 3 more devices to create false color images. Feel free to check them out. I personally consider the grayscale image to be the more honest representation. Within this video, I will stick to the grayscale representation. By the same logic, we can also implement other parameters, like y2, MPQ, etc. Let's start with y2. We need the fs prime and the fm prime images as input. The formula is essentially the same as for Fv over Fm. The next devices are the same as for Fv over Fm. I will add them later. Next, I like to add NPQ. We need Fm and Fm prime as inputs here. The formula is slightly different here. The formula is Fm minus Fm prime divided by Fm prime. Hence, A minus B divided by B. The next parameter I like to add is F0 prime. With some protocols, this parameter is a measured parameter. If it's not measured, like here, then we need to calculate it by this formula. We need F0, Fv over Fm, and Fm prime as inputs. We have 3 inputs. The last parameter I like to add in this video is QP. Here we need F0 prime, Fs prime, and Fm prime as inputs. The formula is simpler now. You see, you can use earlier calculation results as input to more complex parameters. Now we need to copy the final section over from FV over FM. As I said earlier, we use for NPQ, F0', and QP the merged segmentation. As I said earlier, with NPQ, F0', and QP, we'll use a merged object list from the merged segmentation because they use inputs originating from earlier and late measurements. Since the range of the possible values is different for each parameter, we need to check the amplification factor for each of them. 255 is good for NPQ. If we copy a writer device, it gets automatically a new name. And this name is written in the caption as well. However, this name makes usually little sense. Therefore, we do the following. We remove the caption and then change the writer label. Doing it in this order is strongly recommended, because the writer label name is copied only to the caption if the caption is empty. Writer label names can only include numbers, letters, and underscore. Only the automatically copied version can also contain brackets. So we have to replace the prime by a P. The amplification of 255 is here too large. You watched carefully earlier, 10 is a better factor. .255 is fine here again. For Y2, we will use the segmentation derived from FM'. The amplification of 255 works here good as well. Now let's check the result images. We checked FVO of M earlier, NPQ, F0', QP, and Y2. So there you have it. We have calculated a couple of chlorophyll fluorescence parameters. Using the same approach, you may add additional parameters, including those from later stages of a light curve. In this video, I demonstrated how you can calculate various chlorophyll fluorescence parameters. With this background, you should be able to add more parameters using LemnaGrid if required. One point I didn't cover in this video is how to get the values into the result table. However, this is identical to the way I showed for the color analysis. I featured this in video 3.1.4, LemnaGrid color analysis and greenness. See you in another video of the software and analysis training.